Are looking at graphing rational functions. As a student, your objectives, what I'm looking for you to be able to do, are to determine the asymptotes, points of discontinuities, and the intercepts of rational functions, and then to also graph rational functions. And this video is going to be a two-part video, so we're going to do most of this in the first video and then do the remainder and more practice in the second video. So let's get started. All right, I want to begin with this introduction, going back to Algebra 2 and a concept that was taught. It was dividing different polynomials, and specifically dividing a polynomial by a linear binomial. So in this case, you have this quadratic divided by x plus 2. And you have then in part, the second one here, you have a cubic function divided by x minus 1. And we learned how to divide these using a nice algorithm. It was called synthetic division. And in your notes, I made a reference to it. If you've forgotten how to use synthetic division or you need a little recap, please go rewatch that video and then try to do these two problems. The correct results when you divide, the result for the first would be 2x plus 6. It divides evenly, so that means that x plus 2 is a factor of that quadratic. And for number 2, x minus 1 is not a factor. It doesn't divide evenly. You're going to have a remainder when you do that division. All right, so now with that in mind, that's going to be something we use throughout this section. A rational function can be expressed as the quotient of two polynomials. You see now why we're going to need to do division. It's the quotient of two polynomials where the function p and q are each polynomial functions, and q cannot be equal to 0 because that would mean that your function was undefined there. So let's first discuss what discontinuities are. The zeros of your denominator indicate discontinuities in your graph, and there are different kinds of discontinuities. So in this first example here, this first picture, for function f, you see that there are both vertical and horizontal asymptotes. And the function f has what is called a non-removable discontinuity at its vertical asymptote, which is x equals 0. That is where your function is undefined. In this function called g, it's 5x over x squared plus 1. This function has no discontinuities because your denominator can never equal 0. Whenever you square something, it makes it positive, and then plus 1 is going to make it even more positive. So there's never going to be a time here when your denominator is 0. And because of that, we have a continuous function, and you can draw it without lifting the pencil from the paper. See, continuous functions, that's kind of like a continual line, you could think of it. And discontinuities means that it's not continuous, discontinuous. You're going to have a break in your graph. You have to pick up your pencil. So this one is continuous. G is continuous. Let's look at H. H is discontinuous. It has discontinuities. You'll see that it has a break at an asymptote, but it also has something else if you look over at the x value of 3. If we were to factor this h function, the denominator would be x minus 3 and x plus 1. And that makes sense now why you have a vertical asymptote at 1, right? Because it has, if you plugged in -1, it would make it undefined. But where's the vertical asymptote for x minus 3? Well, look here, you could cancel those out. You can remove that factor, and the result, h, can really be written as 1 over x plus 1, and we have to include that x cannot equal 3 because the original, before we simplified, that was a factor, but we removed that factor to simplify our function. And when you do that, there it is. So we already have noted that we have a non-removable discontinuity at your vertical asymptote. But when you remove a factor from the numerator and denominator, when you can simplify that, that results in point discontinuity at that removed value, which in this case was at when x is equal to 3. And what is generated is something that looks like a hole. All right, so those are the types of discontinuities. A vertical asymptote is one of the discontinuities, and it will occur at any zero of q, which is your denominator, that doesn't have a matching zero in p. And point discontinuity, or a hole, will occur at a zero of q at a factor in the denominator of q that cancels with a zero of your numerator. That is where a point discontinuity will occur. So let's determine our discontinuities in this first graph here, in G. To be able to do that, we need to factor and simplify if possible. So factoring the denominator, that quadratic can in fact be factored. You can use the cross method, and the result will be 2 binomials. It'll be x minus 3 and x plus 1. Now you can simplify. There is an x plus 1 in the numerator and denominator, which means we can rewrite G as 1 over x minus 3, where x cannot equal -1 because that -1 is the zero that we canceled out from the numerator and the denominator. It's the value of x that would have made the original undefined. Okay, so now let's interpret what this means for us, where and what kind of discontinuities we have. We have point discontinuity at that removed zero, which is at -1, and we have a vertical asymptote at the line x equals 3. All right, so those are discontinuities. Now let's talk about horizontal asymptotes and how the degree of your numerator compares to the degree of your denominator. That's going to determine the type of horizontal asymptote. I'll say that again. How the degree of your numerator, p, compares to the degree of your denominator, q, is going to determine your asymptote. So if the degree of p is less than, you're going to have a horizontal asymptote, and it'll be the line y equals 0. Take, for instance, this graph here. The degree of the numerator is 0. You do not have you don't have x raised to any power. It's just a constant polynomial, which means it has a degree of 0. And in your denominator, your degree is 2 because x is raised to the second power, that is the highest power. Because your numerator's degree is less than your denominator's, you're going to have a horizontal asymptote. Okay, so another scenario. What if they're equal to each other? When they're equal to each other, you're going to have a horizontal asymptote, and it's just going to be the line y equals the leading coefficient of your p function divided by the leading coefficient of your q function. So here we go. We have g, and both the numerator and denominator are linear polynomials, meaning it's x raised to the almighty 1. And that means that the horizontal asymptote is at your leading coefficients. So that would be -3 divided by 2. -3 divided by 2 is where that horizontal dashed line representing your asymptote is graphed. All right, last situation. What if your numerator's degree is greater than? When that happens, you're not going to have a horizontal asymptote. Take, for instance, this one. In your numerator, you have a quadratic. Its degree is 2. And in your denominator, it's linear. Its degree is 1. And so it's not going to be a horizontal asymptote. It's actually something different. It's called an oblique. Oblique meaning slanted asymptote. And in our next video, we'll discuss how to find your oblique asymptote. So let's do this. Let's identify the asymptotes and graph G. To do this, we need to figure out our discontinuities, and that will give us the ability to find any vertical asymptotes or point discontinuities, which we need to show when we're graphing. So the denominator can be factored to x minus 3 and x plus 3, which means you have a vertical asymptote at the lines x equals 3 and x equals -3. There's no point discontinuities because you cannot remove factors. All right, now your horizontal asymptotes. Horizontal asymptotes, you look at the degrees of your numerator and denominator. And because the power or the degree of your numerator is quadratic and of your denominator is quadratic, it's going to be the ratio of those leading coefficients. So that would be 3 over 1, which is just 3. So when you graph it, you're going to have your vertical asymptotes at -3 and at +3, the vertical lines, and you'll have your horizontal asymptote at y equals 3. And to find the shapes of the graph in those other, where you see in the dark blue, that is done just by picking values and plugging them in using your table of values. You would take x at -4, plug it in, and the result is 1, 2, 3, 4, 5, 6, 7. So that is how that is done. If you have a question about using your calculator or doing that on scratch paper, make a little note in the margin and I'll be sure to show you that. All right.